correlation coefficient. And in some cases, you probably have seen the Kramer's V correlation coefficient. I'm going to give formulas for all these now in a moment. Yeah, the Kramer's V correlation coefficient, and then in some other cases you probably are familiar with seeing the phi correlation coefficient. Okay, now all of the other cases are a little bit more exotic. Okay, and we probably aren't as familiar with seeing them. But the important point I'm trying to make here in this particular video is that depending on the measurement scale associated with your variable, there is an appropriate correlation coefficient to use. Okay, and it's not good enough just use Pearson's or to use Spearman in all circumstances. Okay. Uh, so let's have a look at another one that might be more familiar to us. If we're dealing with a dichotomy, okay, we have a natural dichotomy like males and females, okay, is one variable, and then we have an interval stroke ratio scale of measurement associated with the second variable. Well, the correlation coefficient in this particular instance is what's known as the Point-Biserail. So it's called the Point-Biserail correlation coefficient, and it's typically symbolized by RPB. Okay? Now, you might ask yourself the question, well, say if I have a variable, okay, that's measured on an interval stroke ratio scale of measurement, and I want to split it up into two groups. Okay? So there's a transformation being made of the pure continuous variable, and your observations are being split into two particular groups, into a dichotomy. In that particular case, the appropriate correlation coefficient to use isn't the Point-Biserail, okay? It is actually what's known as the biserial correlation, which is just biserial, okay? The biserial correlation, and symbolized by R or B for biserial. That's where the variable that has been dichotomized artificially, okay, is associated with a continuous variable. And there's also other restrictions. This continuous variable needs to be relatively normally distributed as well for these particular formulas to work. But in the pure case where we have a pure dichotomy associated with an interval variable, the formula is known as the Point-Biserail correlation coefficient. And they're the main ones. I suppose we have one other, which is when we have a multichotomy associated with an interval stroke ratio scale variable, and the correlation coefficient associated with that is what's known as eta. Yeah, okay? And the formula, well, it could either be something like this, small Greek epsilon for eta, or we have the eta, we have the eta symbol letter there. Okay. Now, you might ask yourself, okay, well, what about the scenario? What about this particular scenario here? Okay, this particular scenario here where we have a dichotomy along with a multichotomy, and this particular scenario here where we have a dichotomy along with a rank with an ordinal variable, or say we have a multichotomy along with a rank, or if we have a rank along with an interval with a scaled variable, what is the appropriate correlation to use in them particular cases? And I have got 4 other correlation coefficients I'm going to show you now in a moment that fit into these particular categories, but there's no real names actually associated with them other than, let's say, from Weary's perspective, this correlation is known as let's say RMD. This correlation here is known as RDR. Okay. This correlation here is known as RMR, and this correlation here is known as RI for rank and interval. So effectively what we have, don't forget these over this side here are basically repeated because the correlation is typically symmetrical. So if I'm looking for a dichotomy and a multichotomy, well, that's the same as a multichotomy. Excuse me. If I'm looking at a dichotomy and a multichotomy here, that's the same as the dichotomy along with the multichotomy here. So let's have a look at the formulas. And I'm going to start off with the typical ones. I'm going to move in this particular direction. I'm going to just, let's say, do this one here first, followed by the Spearman, followed by Kramer's, followed by phi. Then I'll give you the Point-Biserail, which is our fifth, followed by eta, which is our sixth. And then I'll give you the four, let's say, what Weary classified as the missing formulae. So there's four formulas that Weary has presented in his book, Contributions to Correlation Analysis. So let's start off here with these particular formulas and let's see how we get on. Okay. So the first one is, well, it's a straightforward one. It is Pearson's. So we have it's the Pearson uh, rank product moment correlation coefficient or, and we know that that's for an interval with an interval variable. Okay, so when we're dealing with an interval versus an interval variable, okay, well, the correlation or is simply defined to be the covariance of the x variable along with the y variable divided by the sample, let's say, standard deviation of x's along with the sample standard deviation of the y's. And there's many ways to write this particular formula. You've probably seen this in a different form, maybe like something like, let's say, n times sigma xy minus sigma x times sigma y all over n times sigma x squared minus sigma x all to be squared times n times sigma y squared minus sigma y all to be squared, and it's the square root of that thing there. Okay, so it's quite a vicious looking formula, but effectively it's just a covariance divided by the standard deviations associated with the product of the standard deviations of the x's and the y's. That's Pearson. In relation to Spearman, so the Spearman rank correlation coefficient, what's that for? That's when we're dealing with a ranked variable along with a ranked variable. Okay, so we're talking about ordinal versus ordinal. Okay, and the formula that we have in that particular case